Hello, I am Dr. Ray Wyman, a retired astrophysicist. The website you see here, in yellow, is devoted to climate science education. A feature of this website is a series of tutorials on climate science basics. I especially hope that junior high school, and junior college science teachers will find them useful. This video accompanies the fourth such tutorial and is devoted to explaining how the greenhouse effect works. The greenhouse effect is fundamental in understanding the changes in the Earth's climate as a result of human activities. It's been well understood for well over a century. Despite this, there is misunderstanding of how it operates. Indeed, there are some, including a well-known TV weather personality, who even deny its very existence. To explain how the greenhouse effect works, I've created a little movie that simulates how infrared radiation flows through the Earth's atmosphere. But before seeing that, we need to describe some basic physics involving radiation. By radiation, I mean light waves and their extension to longer wavelengths that we call infrared radiation. Until the beginning of the 20th century, light was thought of as consisting of waves. But with the discovery of the photoelectric effect, it was realized that radiation has both a wave and a particle aspect. In describing the interaction of radiation with molecules, it's best to use the particle description. These particles are called photons. They're bundles of energy traveling at the speed of light. The laws of quantum physics allow molecules to have only very specific amounts of energy. They can vibrate with certain definite amounts of energy, just like piano strings can vibrate with certain frequencies. In addition, molecules can rotate with definite allowed energies. Molecules can increase their vibrational and rotational energy by absorbing the energy of a photon that strikes it with just the same amount of energy that corresponds to the molecule's energy increase. You can think of molecules as being little targets that a photon may strike, but the area of the target depends strongly upon the particular change in its vibrational and rotational energy when it absorbs a photon of that energy. Here is an animation illustrating this. This represents a carbon dioxide molecule with two oxygen atoms on either end and the carbon atom in the middle. The white lines represent the electrical forces holding the molecule together. Now I'm going to launch a photon towards the molecule, and you'll see its energy transformed into vibrational energy. A photon with slightly different energy would give it some rotational energy also. Now I'm going to pause here for a moment to explain that if the molecule is left alone, the reverse process would eventually occur. The vibrational and rotational energy would be converted into another photon, emitted in a new random direction, maybe up, maybe down. But more often than not, before that happens, because of the huge number of molecules and even a tiny volume, along might come a nitrogen molecule colliding with our CO2. Here come one now. The vibrational and rotational energy of the CO2 molecule is transferred into increased translational energy of the nitrogen molecule. You'll notice that the nitrogen molecule leaves with more rapid motion than before the collision, and the CO2 molecule lost its vibrational energy. This process also occurs in reverse. Another nitrogen molecule having a larger than average amount of translational energy can give up some of its energy to deliver vibrational and rotational energy to the CO2 molecule. But before saying goodbye to our nitrogen molecule, you might wonder why it isn't also able to absorb or emit infrared photons like the CO2 molecules do. In fact, nitrogen, along with oxygen molecules, do emit and absorb radiation, but only the incoming harmful and much more energetic ultraviolet radiation from the sun. Without going into the details of quantum physics, the reason they don't absorb or emit the less energetic infrared photons emitted by the Earth has to do with their simple symmetric structure. This is in contrast to more complex molecules like CO2, water vapor, and methane. In summary, the processes we have just described distribute energy among all the molecules in the atmosphere, but it's only through greenhouse gas molecules like CO2 that energy is exchanged between the infrared photons and the molecules in the atmosphere. To create a movie of the greenhouse effect, I've imagined a toy molecule here that qualitatively resembles a greenhouse gas molecule like carbon dioxide and the infrared photons that interact with it. I've color-coded these photons, of course. They don't represent real colors. It's just a way of representing slightly different energy photons and the corresponding slightly different energy changes of the molecule. The red photons interact very strongly with the molecule, and the strength of the interaction is represented by the height of the red bar. Yellow photons, with slightly different energies than the red ones, interact less strongly, and the white ones even less strongly. However, when a photon of any of these energies is absorbed by the molecule, collisions with other molecules shuffle the various combinations of vibrational and rotational energies about. From time to time, the molecule will emit one of these infrared photons. In my toy molecule, it is 4 times as likely to emit a red photon as a yellow one, but there are twice as many yellow combinations of vibrational and rotation energy changes to choose from. So the result is that for every 4 red photons emitted, 2 yellow ones are emitted. Similarly, for every 4 red photons emitted, a single white one is emitted, even though the target area for the red photons is 16 times that of the target area for the white ones. The bottom line in green represents the emission of photons from the Earth's surface. Here the situation is very different. The surface of the Earth consists of molecules of rock or water that are so squished together that separate energy states disappear. That means that the warm surface of the Earth gives off a continuous energy range of infrared photons. The rate of this emission depends mostly on just the surface temperature. In this case, the larger spread of energies, represented by the white photons, means that for every red photon emitted by the Earth's surface, 2 yellow and 4 white ones are emitted. Of course, some photons hardly interact at all with molecules in the atmosphere and stream freely into space, and those are the ones I've represented by the green rectangles. This image emphasizes that the 3 colors of photons travel, on average, very different distances before being absorbed by our toy molecule. The red photons travel, on average, only 1/4 the distance of the yellow ones, which in turn, on average, travel only 1/4 the distance of the more weakly interacting white ones. These are averages, however, and it is the luck of the draw how far a photon, say a yellow one, will travel before being absorbed. The yellow curve here represents the probability that a yellow photon will travel a certain distance before being absorbed. Imagine that we launched a large number of photons through an absorbing gas. By the time they have traveled this distance down here, about half of them will have been absorbed. By the time they have traveled this distance over here, about 30% will have survived, and just a few percent will have managed to travel way out here. This probability curve is called exponential decay, and it's the same law that governs how radioactive atoms decay. In an appendix to the tutorial accompanying this video, I explain the origin of the law of exponential decay. Now I'm going to show the little movie I've been speaking of, but before I do this, I need to explain that in this simulation, I've assumed a horizontal distance of 50 miles and a vertical distance of 10 miles. But to make it easier to follow the paths of the photons in a vertical direction, I've stretched the vertical scale, as you can see. So instead of 10 miles being this high, it's only this high. This distorts angles and makes it appear that photons move faster up and down than sideways, but of course they all move at the speed of light. I've used what's called a Monte Carlo simulation to make this movie, and details are described in an appendix to the tutorial. Additionally, I've assumed a condition called radiative equilibrium. That simply means that every little box in the atmosphere is in energy balance and that this energy balance involves only absorption and emission of infrared radiation. So every absorption in every little box must be balanced by an emission. I'll comment later on how the real atmosphere differs from this assumption. Okay, here we go. You can see the red, yellow, and white dots representing photons emitted from the surface and traveling through the atmosphere. I've marked their absorption by the greenhouse gas molecules with a little splat. In accord with our model, the white ones generally travel the furthest distance before being absorbed, and the red ones the smallest. When any photon is absorbed, red ones are more frequently emitted, but the white ones are the most numerous ones emitted by the surface. I haven't shown the green photons. They're not very interesting since they immediately escape to space. Most of the absorption takes place near the surface where the atmosphere is dense, and therefore so does most of the emission. Such an emitted photon has a good chance of being sent back to the Earth's surface, and this is called back radiation. This back radiation is the essence of the greenhouse effect. Instead of all the energy that is emitted at the surface escaping, part of it is returned to the surface. At high altitudes, the atmosphere thins out and the paths become longer and escape is more likely. White photons most readily escape, while red photons rarely escape unless they are emitted far above the surface. Because of the condition of radiative equilibrium, the number of escaping photons plus the number of back radiated photons must equal the number emitted from the surface. But the net flow of energy, up minus down, is always upwards, and it's the same at the surface as it is at the top of the atmosphere. This image will explain how the transfer of infrared photons through the atmosphere is connected to the temperature at each layer of the atmosphere. But first we need to discuss briefly what we mean by temperature and what it measures. Temperature is a measure of the average energy of all the individual molecules. This includes translational energy as well as rotational and vibrational energy. But temperature also describes how energy is distributed among the collection of molecules. At low temperatures, for example, very few of the CO2 molecules have enough vibrational energy required to emit an infrared photon. But with increasing temperature, a larger and larger fraction of them will have this energy, and thus with increasing temperature, the gas can radiate more energy away as infrared photons. The temperature at each layer of the atmosphere is determined by the condition that the rate at which the layer radiates energy balances the rate at which greenhouse gas molecules in their low energy state absorb the energy of the infrared photons. So what determines this rate of absorbed energy? In this image, I've taken a snapshot of a simulation with a lot more photons in it. It gives an idea of how dense the swarm of photons is at each level of the atmosphere. The denser the swarm, the higher the rate at which photons will be absorbed in that layer, and thus the higher the rate at which they deliver energy to it. So the density of the photon swarm is directly related to the temperature of the atmosphere at every level. You can see that the swarm is densest at the bottom and drops off with altitude as we expect. Simulations with a very large number of photons show that the swarm density, and therefore the temperature, drops off quite steeply near the surface. Half of the photons emitted from the surface make an angle of 30 degrees or less to the surface. This means they are absorbed quite near the surface because of the long, slanting path they follow. I'll discuss the implications of this steep drop-off in temperature near the surface after we tally up the results of the simulation we've just watched. For our toy model molecule, we present the results by simply counting the number of each of the colors that escape and the number that are back radiated. The blue line represents the Earth's surface, and the area of the solid rectangles labeled surface radiation represents the number of photons emitted from the surface. The magenta line represents the top of the atmosphere, and the area of the solid rectangles labeled escaping radiation represents the number of escaping photons. Not surprisingly, the red photons have the hardest time escaping because of the short distances traveled before absorption. Similarly, the crossed-hatched rectangles represent the back radiation absorbed by the Earth. Again, not surprisingly, the red ones are most strongly back radiated. The dip in the escaping radiation has been observed by satellites looking down towards the top of the atmosphere, and the back radiation has been observed from the ground looking up at the atmosphere. Both these observations agree well with detailed calculations as described in the next post in these tutorials. Because we've imposed the condition of radiative equilibrium, the total number of emitted photons that fail to escape must be equal to the total number of photons which are back radiated. I mentioned the steep drop in temperature near the surface that one expects if the atmosphere were truly in radiative equilibrium. In that case, warm and moist blobs of air are able to rise up from the surface and add to the energy delivered to the atmosphere by the absorption of the surface-emitted photons. This process is called convection, and it makes the actual drop in temperature with height less steep. I briefly discuss convection in the tutorial post accompanying this video. However, it doesn't alter the basic mechanism of the greenhouse effect. To illustrate this, I've used the same toy molecule to compare how the photon flow is affected by the additional transport of energy associated with convection. As this image shows, the greenhouse effect is still very much in evidence. Now, however, there is an additional flow of energy from the Earth's surface, represented schematically by the light blue rectangle. This heat energy, carried by convection, is delivered to all the molecules, and it amounts to about 20% of the photon energy radiated from the surface. This means that the number of photons escaping, plus those back radiated, now exceeds the number injected from the surface. 20% happens to be about what actually occurs in the atmosphere, but our simple toy molecule underestimates the amount of back radiated energy. Calculations taking into account the hundreds of thousands of different photon energies that can be absorbed from the many types of absorbing molecules, especially water vapor, have been made, and these calculations agree well with observations. But to do this requires a lot of work and a lot of computing power. An interesting fact is that on average, the energy delivered to the Earth's surface from the infrared back radiation is about twice the amount directly delivered to the surface from sunlight. In addition, detailed calculations take into account another phenomenon. The atmospheric temperature at first drops with altitude, as we know, but somewhere between about 30,000 and 55,000 feet, the temperature levels off at 60 or 70 degrees below zero and then actually rises. This leveling off and subsequent rise in temperature is the region of the atmosphere called the stratosphere. I briefly discussed the stratosphere in the tutorial, but this too does not affect the major features of the greenhouse effect. In the simulations I've shown, the computer program generates a given number of surface photons and tallies the number of escaping photons and the number of back-radiated photons. We could change the amount of absorbing greenhouse gas molecules and then generate the same number of surface-emitted photons and see how the fraction of escaping and back-radiated photons changes. But this isn't really how nature works. To provide a better understanding of the relation between the greenhouse effect and global warming, imagine a situation in which there were no greenhouse gases in the atmosphere at all. The right portion of this image shows the situation. All the infrared photons emitted from the Earth's surface directly escape to space. Since the Earth's climate system is never far from being in energy balance, the amount of escaping energy, represented by the area of the rectangle labeled no greenhouse gas, must balance the energy input from sunlight. Suppose we add greenhouse gas molecules to the atmosphere, leaving the amount of incoming energy from sunlight the same. Now, less infrared energy escapes, and the back radiation warms the Earth. This increases the surface temperature, and thus the number of surface photons being emitted. This is shown in the slightly higher level of the left-hand side of the image, labeled surface radiation. Energy balance is restored when the combination of this increased surface emission and the decreased number of escaping photons balances the incoming sunlight. The net result is a warming of the Earth's surface. With this background of how the greenhouse effect works, let's conclude by addressing three of the most common myths concerning the greenhouse effect. Experts in communicating climate science to the public caution that one must be very careful in discussing these myths. It's important to emphasize the correct science and not the myths. Otherwise, people often remember the myths as facts. So I have put the myths in small red font and the correct science in large, bright yellow font. So here is the first myth. It has sometimes been alleged that the greenhouse effect would violate the second law of thermodynamics. Here is the truth. The greenhouse effect absolutely does not violate the second law of thermodynamics or any other law of physics. It is an observed fact. This myth probably arose because of a misconception that in order for some energy to be back radiated to Earth, the atmosphere would have to be warmer than the Earth's surface, which it is not. There is still a net positive flow of energy from the Earth's surface to space. Here is the second myth. You sometimes see this myth stated by saying that if there were 10,000 pennies, each representing a molecule in the atmosphere, that only 4 of these pennies would represent carbon dioxide, and it is thus argued that CO2 molecules can have very little effect. But we've seen that the role of molecules, like nitrogen, is simply to distribute the energy absorbed by greenhouse gas molecules among all the molecules in the atmosphere. Nitrogen and oxygen play no role in the energy input and output of radiation. All that matters in the greenhouse effect is the number of greenhouse gas molecules above the Earth's surface. The recent health crisis in Flint, Michigan, involving lead in drinking water, illustrates the absurdity of saying that just because the fraction of a damaging substance in a sample is small, that substance can have no significant effect. If lead levels in our drinking water comprise the same fraction as the fraction of carbon dioxide molecules in the atmosphere, then the lead in the water would exceed the dangerous level by about 25,000 times. Would you drink such water? Here is the third myth. With increasing CO2 and other greenhouse gases, the fraction of energy emitted by the surface that is back radiated increases. So you might think that adding more would eventually have little effect. However, with such an increase, the level in the atmosphere from which photons of a particular energy can escape must also rise. But the temperature doesn't drop to absolute zero, so some photons are always emitted even from these upper levels. More importantly, with increasing amounts of CO2, absorption of photon energies that are unimportant at present amounts eventually become important, and even our green photons start to be absorbed. Over a moderately large range of CO2 concentrations, every doubling of the concentration produces a roughly equal increase in the greenhouse effect. But even doubling CO2 from its pre-industrial value of 280 parts per million will bring very serious consequences. We're already feeling very significant effects from greenhouse gas warming, even though the CO2 concentration has only increased 40% from its pre-industrial value. The planet Venus is the poster child for the greenhouse effect caused by CO2 absorption. Venus has roughly 160,000 times more CO2 molecules above each square inch of its surface than the Earth has above each square inch of its surface. This results in a scorching surface temperature on Venus of about 860 degrees Fahrenheit. Incidentally, another myth propagated on a popular denier website is that this very high surface temperature has nothing to do with the greenhouse effect, but is simply a consequence of the enormous atmospheric pressure on Venus. In the next tutorial of this series, I'll compare Venus, Earth, and Mars and explain why that is a myth also. I'll also discuss greenhouse gases more generally, with special emphasis on the role of water vapor, carbon dioxide, and methane. Here are two references for those wishing more information on this topic. The first is an excellent summary in the publication of the American Physical Society by a leading expert in the field. I highly recommend it. The second reference, by climate scientist Rasmus Benestedt and his colleagues, is another way of describing the greenhouse effect. It appeared in the February 12, 2016 post in the Real Climate website, a wonderful source of information on all aspects of climate science. My own view is that what constitutes the best explanation for a scientific topic is a matter of taste, and different individuals will prefer one explanation over another. I've chosen the simulation approach because it models fairly accurately how photons actually flow through the atmosphere, but I encourage readers to also consult this reference. This concludes our video describing the greenhouse effect. Thank you for watching it. Please send questions or comments to the website indicated, and I'll do my best to respond to all of them, provided only that they are reasoned and civil.